Everyone, this is the conference for artificial intelligence, beyond artificial intelligence research, a new innovation and industrial domain. So this is what we are talking about, and after the break, the first speaker is Botond Cseke from Volkswagen DataLab Munich, who is a local anyway, but came here to us to share recent ideas. So the floor is yours.
Thanks a lot. Thanks for the invitation. Happy to be here. My talk is going to be a bit more technical because I think I've prepared it with a different room in mind. So I'm going to talk about recent advances in 3D generative models. Okay. So I'm going to show you two papers and what's the actual state of this domain. And basically, these are two foundation models that are used almost everywhere lately. And we are also using it within the company to build applications around and to fine-tune them and so on. So it's not going to be anything particular to Volkswagen, but I'm going to touch upon the things we are doing there with these models. So if you just open your phone and then you have a very nice picture of yourself and you'd like to know how this coat is going to look on me, then you can go to Google and take the guy from the website, take yourself, and then basically just transfer the coat to myself or something like that. And then there you go. You can have a coat which basically is transferred for the first one to the second one. There are a bit of glitches. As you can see, the position is fine, but it also transfers the hands with the code, so it's a bit tricky, but it still does something meaningful. And so there are also other models, for example, Flux, which is like one of the top image generation models, text-to-image generation model. And there's also multimodal Llama, where you can basically plug in a picture and ask questions about the picture. So these are models that are trained with billions of image and text pairs. And this is one of the disadvantages of the 3D models, because they actually don't have this amount of data. So people don't go around during the holidays, create 3D models, upload them on Instagram and Facebook. So whatever these companies have in terms of data, it's very unlikely to be gathered in the same way for 3D data. Also, it's a bit tricky because everything that's around us, from the components in your mobile phone to the rubber on your shoes, has a 3D model somewhere, because someone has created a CAD model, had to print it, had to manufacture it in some way. So these models are sitting around. We just can't use them because evidently these are under patents, licenses, and people don't want to give them away for free. So what can we do then? There are some data sets which are like Objaverse, which has a bunch of 3D models, but these are mainly from video games. Then also there's an Amazon Berkeley objects data set. There's toys. Some people have tried to reverse autos, basically take cars, take them apart, scan the components. And then we also have a bunch of CAD models, which are probably the most important ones. But they're very simple, and there's also a very limited amount of data. So there's only, for example, you have 10 million models from games, and you only have around 700,000 of CAD models, which are simple components like screws or small little boxes and box-like objects. So what can we do with this data? So people nonetheless try to do something with it, and came up with some nice models. So first of all, let's focus on what exactly the data is. So data can come in a lot of different flavors. One of them is, so the easiest one is just a bunch of pictures from different angles, and then a scene can be represented as a collection of these images with known positions. And the second one, can be used for learning scenes and rendering them, but it's not that useful. What is most useful is, for example, point clouds that are gathered by LiDARs and all kinds of other scanning procedures, and often come as points with, sometimes they come with normals, sometimes they come with intensity values and so on. So the next most important thing that's really useful in industry are these two. So there are the meshes, which basically have a proper geometry. So there are faces, vertices, edges, and faces. And the best ones are obviously the CAD models that they use in computer-aided design. So there you have vertices, edge curves, faces, and these are all specified by exact models like spline, patches, and so on. So this is how the data comes to us, and then the question is like, what can we do with this? How can we represent these things in a computer, right? So, so then we come to representation, which is a bit different than what Stefan said earlier. So this is going to be my representation, and the representation he kindly introduced in my talk is going to be something called the latent space. So these are like implicit fields, which are basically like a surface in geometry. It has positive values on the positive side of the surface and negative side on the negative side of the surface. So all we want to do basically is learn a scalar field, and then it can be a neural network which we query with a point, and is going to say, okay, is it on the positive or a negative side of the surface? So the next one is 3D Gaussians. So these are similar to point clouds. Their advantage is that in the same way like point clouds, we have a bunch of points in the space, but instead of points, we have proper Gaussians, which have color values, shades, and so on. And so we can represent a scene by a bunch of little Gaussians spread over the space, and it's super easy to render them because we basically create a plane. We project all these Gaussians on it, and there we go. So we can have a scene and render it super fast. And so in my talk, I'm going to focus on, there are other ones as well, but in my talk, I'm going to focus on these two meshes and the Gaussians. Okay, so how would we want to use this in industry? It would be nice to use it, for example, to turn sketches into design. So in the design, we would also like to use them to create objects in a simulation, right? So you have a simulation running. I need something. I look at an image, click on it. I create a 3D object and put it in my simulation. Now it depends what I want to use for. Like sometimes I want to use only for rendering. So that in the simulation I have a rendering and I have an image, and I can use it for something else. In some other cases, I actually want to use it, the object, to interact with something. So in, for example, finite element methods, crash test simulations, and like those type of simulations, and so on. So the current problems with these models are that whatever we generate is not accurate enough. The geometry they generate, especially the meshes, come with a lot of disconnected components, some triangles that are quite degenerate, so they don't have nice uniform faces. And the 3D Gaussians are only used for rendering. We cannot actually do anything with them. So, good. So the question is like, how do we generate data? And the two things that we are looking at is how do you generate data from images, and how do we generate data from text? And possibly, how can we generate something and then reactively manipulate, say, I want to change something on this model, and so on. So let's jump into this. What the goal is, what are generative models? Generative models are basically some sort of mathematical functions that takes a code, a condition, and it adds some stochastic source and generates something. Like, for example, in this case, the digits. Like we have, for example, a Gaussian noise. We put it to this, and the digit that we want to generate, we put it to this generator, which is just a function or a neural network or whatever it is, a universal approximator. And then basically we want to generate samples that are similar to the data we have seen. And there are a lot of ways to define similarity. And in most cases, if we have a probability distribution that we can actually compute, then we can do maximum likelihood. We just tune the parameters such that we plug in the data in the model we generate. If that's not possible, then we can if we can only sample, for example, then we can use discrepancy measures, all kinds of empirical estimates of differences between probability distributions, and based on samples. So for example, we sample a huge batch, then we take a huge batch from the data, then we have two distributions given by samples, and then we try to compare them. And then based on that, we define some function that allows us to minimize the parameters of the generator. So that's the story. And then also it's important to point out that the condition, right, and what condition is and why. So if there's no stochastic noise, right, then we cannot generate different objects. So we have to put in some stochastic source to generate different images. And then we have a code, and then we have the freedom to choose what goes where. So if you notice that we have a bunch of slanted digits, then we have borderline, so we can also put this one in the code if we want to. And it goes along with whatever Stefan said, that we want to disentangle important properties of variation and so on. Good, so what we want to do with this one now, we want to generate SDF or some field that describes our object. And ultimately, we want to go through a bunch of voxels, query this field, and then create a mesh. There's an algorithm called Marching Cubes that can do that for us. All right. So how exactly happens this in current models? Typically, as a generator, we have a neural network, and then a lot of people, so very deep neural networks have been used in the recent times that take a lot of space and a lot of time to train, and learning happens through some sort of gradient method. It often happens that for large networks, these kind of gradients either vanish or explode, and learning can be very hard. So for that reason, people try to come up with some methods that don't have to propagate through the whole network. They just have to train locally a bit of the network, one single block, one single layer, and so on. And they ended up, funnily, with ordinary differential equations. And basically what they do, the whole algorithm is like 4 lines of code. And these are the best models nowadays, and then rely on 4 lines of code. So what they do is basically say that I want to take any data point, see how it transforms to see how standard normal noise or a standard normal distribution transforms to this data point, draw this line, and then try to basically, every time I draw a new line, sample a noise, draw the line, and then try to learn the field at an associated point, right? So this doesn't require by propagating the whole generator, but it only requires to evaluate it at a certain point. So what we learn is a field that can basically, at any time and any spatial location, can point us towards something that is similar to the data. So it's that simple, the whole thing. And on top of that, there's also something that Stefan mentioned, so the autoencoders. So it's really hard to generate HD quality images without choosing some sort of relevant, smaller representation. So what happens is that typically we employ an autoencoder. First, we compress the data into some smaller, more manageable size, and then we learn a flow model from it, right? So we learn how to generate data effectively. And so this is exactly what happens nowadays. So we have billions of parameters only for one single bit of the network, and then we reuse that basically all the time. Good. So one of the basic components of these ones are attention layers, which are like composed of 3 things: the value, a key, and a query. So usually value and key go together. They characterize a set data point. And the query, it can be also depend either on the same data or some other data. And what we do is we basically want to generate some weighted average of the values, given how the keys fit to the queries, right? So if you have a query that is similar, produces a high similarity with a certain key, then we pick that part of the data. So this is how we go through, for example, a sentence, right? And then picks the next word. So we look into what's the best next to generate. We look into the history, and what gives a high score, we are going to output that word, for example. In case of images, this holds for features. And so these are like built into blocks, and then huge models are created. But essentially, these are the three components. A flow that generates the data, an autoencoder that generates the latents, an autoencoder that autoencodes the data, and a ton of attention blocks that basically define the architecture of these models. Okay, so currently there are two models out there that are really nice. First one is Trellis. That's from Microsoft, and there's another one, Yunyan. So Trellis has available code. You can fine-tune, download it, fine-tune it, play with it. And Yunyan is only available for inference. So you can use it, but you cannot do anything other than that with it. You cannot train it because the training code is not available. So we kind of use the first one, and then try to figure out what the second one does. So what is Trellis about? So that came out in December last year, and it's pretty recent. So what it does, it basically takes a lot of types of data. Most of the time it's a mesh and a bunch of renderings of the mesh. So what it does, around 150 directions. And what it does, it takes the mesh, it voxelizes it. So it creates basically a voxel space, and then based on the images, the multi-views, it uses Facebook's Dino model to create features. So for each voxel, you have a set of features. And then these are then encoded into some sparse tensors and then decoded, right? So what we end up with is almost the same as the original object, but instead we have features attached to each voxel in the space, right? And then now, so once we are done with this is the encoding, the autoencoding part, you can see that you can take meshes and images, and it produces SDFs, like as meshes. It produces the Gaussians I've mentioned that are useful for rendering, so it produces different types of data that you can use for different applications. So how does prediction happen? So the actual generation, it has two stages. It also has an autoencoder for the actual structure of the mesh, right? So it has like a compact, non-sparse representation in terms of tensors, and it has an autoencoder for that as well. So first, it basically takes some stochastic source, then it transforms it into some latent data that can be then, from which we can generate the voxel structure first, right? And as a next step, then it goes and populates the structure with some features. And then from that feature finally goes to the decoder, and it creates the actual data that we can use. And then so these are all trained with conditioned images conditioned on text and images. So you can choose whatever you want to, whatever conditioning data you want to use. So I'm going to show you examples that are like mostly on images, because that's what. Okay, architecture is a bit complicated, but it's like very standard. So you can see there are a bunch of attention layers, and the model was trained with not that much data. So you can see like up to 12 million 3D objects, and then the voxel resolution is like 64 cube, but then of the latent space, but then the actual voxel resolution you get for this SDF function that creates the mesh is like 256 cubes. Yeah. Okay. So you can generate a lot of fun stuff. You can put in images and then generate 3D models. You can put in text and generate 3D models. So for example, we can take 3 images of a car, and then you can create a 3D model of a car. Then we can put sketches in, and then we generate the same thing. You can download some shoes from the internet, create 3D models. And then you can also download something like that, see what it does with it. This is actually really funny because similar data surely is not in the dataset, but the Objaverse has a lot of 3D models for games. So I suppose this image turns into something like that. Okay. So the other one is this one. I'm not going to have much time for that, but this is a different representation. This uses a point cloud-based representation. Tokens, like Stefan mentioned before. So instead of voxels, we have a set of tokens. And it does the similar thing. And it ends up with a latent that you can query for different voxel values. And it gives you the SDF value. Then you can turn it into a nice surface. So same architecture, it can generate some really nice 3D models for images. And then, so this is basically a comparison of the trellis and this beta model. So you can see, for example, that here, it kind of knows that he has to generate someone with a leg, but the shoes go on the horse, for example, in this case, right? So it sees that there's a person, but it generates the shoes for the horse. So funny stuff. But it knows what the back of the horse looks like. It kind of knows that the person has to be somewhat symmetric, right? So it generates those parts as well. So this is, but yeah, still, the head is like quite close to the body here. Here, it kind of differentiates and then creates a better horse. You can see the back is also much nicer. So it's definitely a better quality model. This one knows what's in the head and turns it into a crown because it's probably a king or something. And this one is a bit better in that respect. Okay, so the second model can also generate a texture on top of the mesh, and then it can produce some quite nice stuff. Yep. Something like that. Good. So this is where these models are. So at the moment, they are really cool to play with. It can be used to help you out. It can help with the design to some degree if you have sketches and so on. But then it really lacks the quality to be used in engineering applications. And what would be great if we could have CAD models to do these things, but we can only have CAD models within the company, but then we don't have the software for it yet. And then we cannot train a model like this within the company, unfortunately. So these are like, I think we would have the money, because you can train one of these like for $500,000 or so on, but no one wants to give it to us, so we can't do it. So we are basically fine-tuning stuff and then digging into the latent space, building applications around, and so on. Thank you. That was all.
Thank you very much. A little bit of technicalities going on. And Andrei, in the meantime, please come and help me. So our next speaker is Andrei Mihai from this university, University of Babes-Bolyai. He is a researcher, lecturer here at the Machine Learning Research Group. So the floor is yours.
Okay, thank you. Yeah. Yeah, all right. Okay, so thank you for the introduction again. I'm Mihai Andrei. So I will present a bit some of the work that we did in the field of meteorology. So this work that we did was part of the WEML project, a project that is a collaboration between our university and two meteorological administration, the one from Romania, ANME, and the Norwegian Meteorological Administration. Right, so what I will present to you is what we did a bit, what data we worked with, what models we have created for the purposes. Well, nowcasting, I will explain a bit. Nowcasting purposes. Yeah, so the goal, well, one of the goals of the projects and some that we worked in is weather nowcasting. So the idea with nowcasting is to try to predict the weather for a very short term. In general, it's defined as 0 to 6 hours predictions. We work to less than 1 hour, so very, very short term, just trying to predict as accurately as possible the weather next time. Well, actually, the purpose of our work was to try to predict radar data. Okay, so how this works is that meteorologists, operational meteorologists, they gather the data from the radars, right? And they try to use that data that they have to understand what is happening and make their predictions, right? So the purpose for the nowcasting models that we're trying to create is to kind of predict what the radar would read in slightly in the future, right? So the purpose of this is to help them. The meteorologist would see, oh, okay, the AI predicts that this will be the situation in, I don't know, 5, 10, 20 minutes. So then they can make better predictions if there will be bad weather or make warnings and so on. So this is the idea that we worked on. Okay, so here I'm just trying to explain a bit the data that we work with. So yeah, in AI research, a lot has to do actually to understanding the data and learning how to work with it, other than just creating the models themselves. So the radar data, weather radar actually gathers data in a certain area on different levels, right? On multiple levels, and what we received as data are multiple matrices, right? Where each point is a physical location on, geographical location, and it says the level there of the data. And yeah, you can see the example there. So each matrix represents one different level of altitude, basically. So we get all of this data every 5 or 6 minutes. So actually the radar gathers a lot of data. We had to understand how to use that data. So also the radar actually creates a lot of different types of data about the wind, about the water droplets, and about everything else that it can find in the atmosphere. What we used is the reflectivity, which is well, basically the water droplets, how big is the water in the atmosphere, something like that. So we have, this is the data that we have. We have reflectivity, which is very useful for meteorologists. We have it on different altitude levels, and we have it every 5 or 6 minutes. So what do we do with it? So first of all right, we can see it like this kind of cubes or images where instead of having red, green, blue, we have each altitude level, and we have these images for each time step, right, every 5 or 6 minutes. So this is all the data that we have. And what we want to do with this is to try to predict the same thing that would be in the future, like the same set of data. So we have the data that is, I don't know, the radar just gathered now. What will the data give, what will the radar give in the next 5 minutes? And this is the very basic case. But then we have like, let's use all the data in the last 20 minutes to try to predict for the next 5, 10, 15 minutes, and so on. So this is, yeah, the models that we created. This is what they are trying to do in general. All right, so now I will go a bit to how we created some of the models. One of them is this Next Now model that we created. It is based on the ResNet. So it is, well, a bit more of a, it's a deep learning. ResNet was a deep learning model that was one of the best models at the time. But yeah, it's before these foundational models and all the other new advancements. So, for example, how we tried to create a better thing for our purposes. So, for example, how research works, as an example here in AI, right? We have this network model has multiple layers, right? And all these layers, well, in ResNet case, they have some kind of blocks that use convolutionals in some way. And what we try to do is to make those residual blocks better by using grouping convolutions instead of simple convolutions, because yeah, that's increased performance and so on. So yeah, the AI research can be done also in these smaller steps. You take a model and you try to update it a bit and make it better for your own case. And that's what we did. Yeah, so how this model worked in general, you can see that it made the smaller, the image, it made it smaller. With, yeah, so the radar data, as I said, we can see it as an image with multiple channels. Instead of red, green, blue, it had then those layers of altitude. And these models try to learn a bit different things about the image, about the shapes, and I don't know, the edges of and whatever things. And we make it smaller, and then we make it bigger to try to recreate whatever it should be in the next 5 minutes or 20 minutes or what we trained the model on, right? So this is the idea of how we trained. It's an example of a model that we made and how we created it based on a different model that existed. And yeah, for example, this is I don't know how well you can see the prediction, but yeah, it's some of the results with the comparison with prediction and observation. And I don't know if you can see, but yeah, one of the problems with the models in general that you have is that predicting higher values of this reflectivity is really hard. Okay, and this is prediction at 15 minutes. It's similar. Okay, I'll just go to the next part. So this is another model. Okay, I guess you can see really well what the model is about. This is a model that we have tried to create ourselves, just some convolutional layers, one after the other. The innovation here was that we didn't try to make the image smaller. We tried to make it, to keep it at the same size, and that made it to learn a bit better the shapes and well, so on. It learn a bit better how weather and reflectivity changes, right? Yeah, but this also increased a bit the computational cost, so we had to make some adjustments, like using different types of layers to make it more better. All right, so this new model, the SEPConv model, is what we use to predict to try to predict up to 45 minutes. But as I said, since we don't make the image smaller anymore, it is much more computationally expensive. So instead, we try to think, okay, how to actually predict all these multiple time steps into the future. So we thought, if we train 3 models, one to predict 5 minutes into the future, one to predict approximately, 15 minutes, and 25 minutes, and then try to combine the results of all these models in order to have a much more linear, to have all the steps that we need, 5, 10, 15, and all the other steps in between, right? So the idea was to have fewer models and combine them to have better, well, to use fewer resources, because we didn't have so many resources to train all these models. So here is, yeah, I've shown there how we combined the models. We had some different ideas and tried some of them, and there are some results on combining, using our tree-based models. Then we combined them in different ways to predict the data at up to 45 minutes into the future. Right, so the idea is that whatever some model predicted, then we use that in a different model to predict even further into the future, and so on. I won't go very much into the details how we combine them, because I don't know if that's, yeah. Okay, so now I show here some performance evaluation metrics. These aren't really important right now, exactly what the metrics are and so on. What I wanted to show you here is how many of them there are, right? So one of the things that we actually had problems with, and this can be interesting in many fields of AI, I guess, is how do you actually evaluate how good of a job you did, right? You have to use some kind of mathematical formula to try to say, okay, this is good or it's not as good. And that is not that easy, right? So there are, we have here three sections of formulas. One is the two sections like root mean squared error or even R squared are some that are very used in computational science, right? But these aren't really made for weather forecasting or for nowcasting, and aren't really that good for that case. So we researched some of them for that case, and we saw that actually used in forecasting is a lot of classification metrics. And well, we didn't do classification, but we tried to change how we measured and how we evaluated our data to try to fit some classification metrics in there, to be able to compare with the literature and to other elements. So like, there are some scores here that are more specific to meteorology, but yeah, there are classifications, which we didn't really do. And then we tried to figure out some image processing metrics. Okay, we tried to figure out, there are all these kind of image processing metrics that we have, if we consider our radar data as images, maybe those are better. And we tried to find out which one would be better. But even that proved to be quite difficult. We actually made a small experiment trying to figure out which would be the best image processing metric by asking multiple meteorologists what their idea was, showing them some images and so on, and trying to find it on a rank base. And so this is how we find these, I don't know if you see visual information fidelity metric. Right, so the idea is that we have all these kind of metrics that all show us something about what we did, but it's really hard to, you know, find out. So here are also the numbers. Again, the numbers and everything doesn't really matter. What it matters is what do we do with these numbers. And actually just having these numbers here doesn't really tell you, did we do a good job or not? You know, just looking at them, you can't really see that. And what you can do is try to compare to related work, right? What did others do? What do other meteorologists, human meteorologists actually do if there are some measures? But measures of human predictions are a bit rarer. It's hard to actually get data of how human predicted and compare the data to your model, AI model, right? And even other, I don't know, other groups in other research labs that did this kind of research on meteorology, they have their own metrics that they used. So we try to, if they used a different metric than us, then we couldn't really compare the results. And even if we could compare the results, it's really hard to say, is it really that much better or not? Because they use different data, right? So some data might be easier to predict than other. They use different methodology and different things. So sometimes it's really hard to compare different kind of what you did to others. And This is a bit what I wanted to highlight here. We have this data, we have these results, and these results, after all the analysis that we could do, tells us that we did kind of a good job, right? Compared to the literature, they're not worse, not also much better, but again, all this comparison is a bit, yeah, it's not quite clear, because again, it's not the same methodology, not the same data. It's hard to really do a good job at this. On the other hand, what these results can show you is tell you a bit how your models work. So again, I don't know if you can see this good in all these numbers, but one thing is that it really showed us that the model have a much higher problem predicting higher values. So higher reflectivity values. Again, reflectivity means how much water is in the atmosphere, right? And meteorologists really care about that the most, because when there is a lot of water in the atmosphere, there is where the storms are and when everything else is, right? And they care much more about that than when there are just a few clouds or there is nothing. So the fact that we actually show that these models work much worse when there is higher level of reflectivity told us that, yeah, there is something that is missing. So it actually showed us a bit just, you know, something about how to try to conduct the experiments further. Right. Okay, and it also showed us that it is harder to predict the actual weather that the meteorologists want than the one that we have. Than everything, right? All right, so this was about the results. Here I will show you some visualization. I don't know if you can see them well, of the observation and prediction. But more than that, I think it will be much more interesting to see a video, right? So on the left side here, you can see the actual data, the real data, and on the right side, you can see our model predicting 20 minutes in advance. So you can see how well it did. Right, is this? It should be a video. I don't know why it doesn't start. Well, for some reason, it doesn't want to work. But yeah, I guess that's it then. Right, thank you.
Thank you. Let's see if just a second if it would work. I don't know, but it doesn't, right? It doesn't seem to be a video. No, it's a PDF. No, okay. You tried and it worked. Okay, it didn't. Okay, no problem. Okay, thank you. So we arrived to the last presentation for today, which is by Lehel Csató, who is the head of DataMin Research Group here in University of Babes-Bolyai University as a professor, and as I said, he really helped a lot this conference to be a possibility, and as we see now, a success. So where's yours? In the desktop. Okay, so the floor is yours.
Hello. Wow, so things work fine. Yeah, thanks for being here. I'm from the local university, Babes-Bolyai, and I speak on behalf of a team which you see on the right-hand side. Hopefully you can see them all. Some of them are here, some of them are possibly online. some of them were here, like Szabolcs. They are former team members. And Szabolcs, please consider the 3 dots on the line behind. That is yours. The talk that I'm trying to give today is about something we started a few years ago. It's called prototype-based decision-making systems. And yeah, let's see just the content. So I will structure it as something like a motivation. Why is a decision has to be justified? What are the benefits? What are the drawbacks? Then I will have one or two slides about why it's important from a legal perspective, if you a little bit zoom out from our technical fields. And then I will try to speak a little bit about the technicalities. Hope I won't be too long. Anyhow, I was told that at 5 sharp, we should stop. I think that this was, well, okay. If not, then I'm a little bit happier. Hope I won't drag you too long on it. So anyhow, and I will draw some conclusions which are mine and does not represent the group or any one of the team members. So first, I would like to start with the issue of the explainability. Like every one of you knows the number 42, which is the greatest number of all. It says that that's the answer to the question, what is the meaning of life, the universe, and everything. And what is said, it's the computer was saying 42, and it said it after 10 million of years of computing. And I find it really metaphorical, the fact that as of today, we're building compute bases that can do literally these 10 million of years of computing in a matter of months. And the promise is that they will be even faster. So then when the computer gives us the 42, and just remember in the matter of months, the question is, so why 42? What does 42 represent? And even in the Hitchhiker Guide to the Galaxy by Douglas Adams, this question, it says that it would require another 10 million of years of computing, but the fact is that the people did not know what they want to ask in the first time, in the first instance. So just to put it back into a much smaller scale, we all know that neural networks are black boxes. So what do we do when we see a decision? How do we interpret it? Are we able to say if things go wrong, why did they go wrong? So these are the questions that we were trying to answer. And if we focus on the image and decisions related to the images, for example, we might say, well, why is that system saying that the road is muddy? Because I see there are some patches which have a certain specifics. Or let's see that, and this is the images are a little bit old, and for most of the people that work with this, it looks familiar. So, for example, what I want to say is that you see there are three images, and the 3 images, the top represents the motorway, and the second is the rural type, and below is something which we call urban type, and the heat maps, they're saying that probably the reason why the classification is such, because the heat map's indicating it. So we want to achieve something like that. Or this is work done by Hanna and Tamás. What do we want? What we do want is that for each class of monkeys, along the lines of saying that is the first type of monkey, the second type of monkey. I'm not a biologist, and I think the first line is an orangutan. The rest no? Thanks, Hanna. So no, it's not. Even that I don't know. But essentially, it's the boxes of which I highlighted only the ones that on the first column, they're saying that we found that as a justifying cause for that image being of a certain class. So just remember, next to the fact that we have images belonging to a class, what we want to achieve is to see why are those images belong to the class, and we want to achieve that adaptively. So this justifiability also comes from a more general point of view, and when I'm speaking about decisions, I'm speaking about decisions in the banking world. For example, you might have a loan approved, or you might have a loan approved with a much higher interest, and it's completely justified that you're asking, why do I get these numbers? And as of today, essentially this act of EU AI Act, European Union Artificial Intelligence Act, what it says is that unless you have systems that have no risk on your financial and health and the other status, you have to have a reasoning, and you have to show every detail that led to the conclusion that you are subjected to. So this kind of an explanation or explanatory mechanisms, they are quite important for also a legal perspective. And in the second part of the talk, I will try to speak about some specifics, a little bit more technical issues that we tried out and we had in the in the explaining of decisions when they were related to the images. So what we did was kind of like whether we can do, we tested whether we can do an architecture modification to a given simple system, and this architecture modification should have the explanation. And those of you who are familiar with it's something in contrast with something which we call the post hoc methods. This is like ad hoc methods and a priori methods. Sorry. So first of the methods that you see is something which appeared in the talk of Stefan, and then later in Botond's speech, was that we should consider some feature vectors, and what you see there is on the red on the right side of the image, and these feature vectors they somehow encode the image, and this is called you can imagine like a loop on the left hand side of the image, and it says, please can I have a feature extracted. Added to these features, there's something which we call the system takes away from some images and takes away something which are called prototypes, essentially a representation of the image, and it says that this image is so important, is so prototypical for the specific class that I better keep it. And also Stefan was saying something about the history of this line of research. Already in the 1980s, that appeared as something we call the radial basis function networks, RBFs, which had the notion of a center and everything that was so the decision was based on the set of centers and some combination of it, usually an exponentiated, a Gaussian Bear curve, and then a linear summation, weighted summation. So just to get how these systems work, it's specifically instructive, and in this case, if the further away you are from the image, the better you can glimpse that on the left-hand side of the bottom image is I think is a puppy, is a small dog, and what you see is that the decision whether there's a puppy or not, there's a dog there or not, is based on the reconstruction, on the feature of which is reconstructed as that blurry image what is seen. So the conclusion is that these systems, these prototypical systems, even if we try to do it well or very, very well, they have a kind of a color and much less a texture, but a shape-based features as a decision. So the improvement that was made is to somehow to consider regions of a bigger image, and there you see there I think is a finch or something. So to consider regions from an image, and essentially these feature vectors of which you saw in these autoencoder type networks of the latent representation, these feature vectors somehow should relate also to the topologies, to the location of those features in the input image. So you can also see that in this the prototypes, they are not only encode the image, but they also encode the region of the image that is interesting to us. So what you had to see is that also they work very close to the autoencoders, and also the prototype layers added to that this kind of locations in these images. And again, what I want to show is that here we didn't need the reconstruction, but what we could do is that we had the kind of a classification, and you see the three classes there on the vertical axis, and the correct was the rural class, which is shown in green, and what we see is that we could also see the justification. So what was wrong is that very often we did this classifications. They were not correct, but nevertheless they were pretty certain that class is urban, and it should have been rural in this case. So what we've done, that was the conclusions that we drew, is that while these prototype networks, they, in spite of the fact that them being good, it's that we might do some other, we call it improvement, and one specifics of the system that we attacked was to see the non-linear type of the backbone, and we said that why not having it something which we call locally linear, and do the decomposition along those lines. So it's a proto-PNet system that we developed. It's done with Tamás Kasta and Hanna Lieb, and she's present here, and then acknowledges to her, thanks to her. And what we've done is that we used kind of a rectangular regions that you see on the image. It's a monkey, I think it's a bonobo. Sorry? Mandrill. Thank you. So it's a mandrill, and every rectangular area is decomposed so that it has a feature assigned to it. The good part is that the decomposition is such that it is invertible. So if you speak mathematically, the invertibility is good because we can immediately identify. So we have no problems with explaining of why is there, because we can always show it. And we've done it with a wavelet decomposition that was supposedly working well for images, and this is a line of research that is done by mathematicians like Dobeshi's or Stefan Mala, just to name a few. And what was that? We could identify next to the correct classification, we could identify the markings, and hopefully you see is a little patchy, but there's an orange or a purple rectangle around the landmarks or the reasonings of why it was the decision was made. Of course, we also had incorrect cases, but overall, what we said that all these methods that we employed, I mean the protopeanut and the wave protopeanut, they were achieving results that were very similar. On a test case of this data set, I'm just foreshadowing that it was from the Bosch company. So the results from this data set were the losses that, as Mihai was saying, they were a little bit better than those of the protopeanut. So just a few conclusions, and once again, these conclusions are mine. Of course, that is what we had, that the prototype-based architectures are a possible direction to explainability. And again, it's better that the prototypes to be simple, and that is a good sign, and is a bad sign also. For example, it is not able to recognize rotations the way it was implemented. And why is that important? Not for the drivers, but if you consider medical images, for example, what we're doing is salivation images and the crystallization, then that's the rotation invariance. It feels like it is a must. Also, from a teaching perspective, I have also some conclusions. We coded in something which is not Python, so we did not have the enormously large code base and library for that. We used something which is called Julia. It's very close to my heart because it's a kind of a functional-like programming, and it's very close to MATLAB, which most of you know, or most of you know with an apostrophe from the statistics or numerical computings. Also, it is interesting that in the last 1 or 2 years, that's a kind of in this GPT and AI for everything. The conclusion was that it was very difficult to get the programmers to do the job or to try to code and interpret the results. And just to say this to you, that I'm speaking about students in the third years of study who worked with me in a group of what we call collective projects, and there was quite a bit of issues with that. Why should we do that? Why is that the results? And they say, and they just did not know it. So with that, thanks, and I just want to acknowledge once more the work of the group. I also want to acknowledge the help from the Bosch. And I acknowledge the HRIA, the Romanian Hub for Artificial Intelligence, which is now the group is part of. So with that, thanks.
Thank you very much. Very nice. So we should have a short question and answer session. I at least have one question. So if the speakers would line up here in this part, and that's what we discussed secretly. So we still have 6 speakers here. So please come up here, and maybe there are questions from the audience, and there's definitely a question from me, at least one. So, yeah, yes. Jó lesz, ott van hang. Yeah, so please, sit down, yes. Up there, yes. You are sitting in the middle, yes, and maybe Geza yes. So, whenever you're wanting to speak, you just have to hit the mic, and that's it.
Hello.
Yes. Have you been sitting here, Roland, as this is your university and your...
Yes, but never. Yes, this is my university, but I never seated in this seat. I was there always.
Okay. Okay. So any questions from the... I have to put your nice pictures up, maybe. I can do that now, just a second. Can I? It is closed. So no, I can't. I will. I have it. Okay. Just a second. So until that, please ask questions, so we can put it out there. Yes. And these are our speakers. So questions from the audience to anybody. It could be about anything. It should be somehow connected to the AI or to today's topics. Who will be the first brave one? Yes, there's a question there.
Yep. So my question goes to Botond. This is, if I understood correctly, all these models that you have presented basically output an SDF, so a sign distance function. And this is not ideal for CAD models, as you've said, because it is not that structured. But CAD models can be represented in other ways. For example, even textually. You could say this is a circle, for example, with a given radius, and etc. Do you know about such research that creates models that output CAD models in such a structured way? Because I guess it would be more efficient.
Yeah. So there are papers. What they basically do is first they output a point cloud. Those are going to be the vertices, and then they create edge curves. So basically curves between them there are edges, right? They can be spline curves, for example. And from this you basically create the, and then for every loop in this graph that you created, then you can have a face, right? And then basically first you create the geometry, the topology, basically, of the CAD, and then after that you fill in all the specifics of the curves, and you use NURBS patches and so on. So there's work on this direction, but it goes in the direction of using sequential models like language models, for example. And the data is super limited, so you have really basic objects, as I said, like rectangles, cubes, few components for different machinery, but it's very far from getting into something like what I've shown you. Yeah. So CAD is the holy grail of 3D models because it has everything that is ready for production, basically. But unfortunately, there's limited data, and the models are not yet good. So this thing goes hand in hand in one way or another, but that's the status. I can point you to a paper later on.
Thank you very much. Thank you. Next question, maybe? The audience? A general question could be as well. No troubles. Not yet. Okay, I have one question on maybe today's topics. So you could be remembering what has been taught today. Maybe one message from somebody else that you learned, if you were paying attention a little bit, either a general message or something that really struck in your mind. So that was really nice idea or nice things that you heard today. Anybody else? Anyone wants to start? Yes, yeah, Lisa.
Yes, this example-based explanation is a good idea, and I like it. Thank you very much.
Okay. So yeah, let's go it like in chain. So then you should.
Well, yeah, I just like the Stefan's talk about these plethoras of models and the duality between the academia and the industry. I think our focus. I was for a very short time a non-academic person, and our focus is always on or my focus person is on the mathematical correctness of something. And when it comes to approximation, everything looks the same, at least for me. And when it's not on the spot, when it's not zero error, then it's kind of people lose interest or just tell me otherwise. But I think the summary was really nice of how to bridge this academia and the industry side.
Okay, thank you. So Stefan?
Works? No, it works. Yeah. So maybe I would mention actually two ideas. So first of all, regarding explainability, that's actually one challenge that I didn't have time to mention. And actually, that was pretty cool what you were showing. And that's actually a very open topic also for us, as you know, from our collaboration, and still unsolved even today. So that's actually something that came up. And also the SDF, the sign distance function idea, which I think in a different context, of course, because I was talking about perception, it is also a point of interest, quite an interesting technique that I liked. Because it's about representation, of course, and it's also, as you mentioned also, like there's this separation between geometry and appearance and so on, which is very important for autonomous driving as well. So, yeah.
Thank you.
At least these two.
So we are going not so around, so maybe Mihai, you want to share?
So one idea, well, one moment that really stuck with me was that explanation of how the machine learning evolved from general machine learning and then to more deep learning and then now to foundational models and how everything is more homogeneous and how this works. That was a really nice explanation of how things worked and so on. So this is one moment that really struck to me. That's nice.
Okay. Thank you. Roland, maybe?
Yeah, so for me it was interesting also to see this talk from Geza about prediction, seeing how predictions about technology might be risky sometimes, but if things do not work out as you planned, it doesn't mean that in 10 years' time it will not turn true, actually. So you should never lose hope in certain things.
Keep working. Thank you. Botond?
So I really like Stefan's talk because it was something close to what I do myself. And then, yeah, I love Professor Nemet's talk because it was a really nice perspective on the historical development of these systems.
Thank you. Anybody coming up with questions? Or, yes, there's one question there.
Hello, I'd like to ask Mr. Roland Witte. I was amazed to see in your talk you mentioned a lot of successful spin-offs. I'd be curious to ask, how do you have so many successful collaborations with the industry, and which one do you think was the most successful among these? Thank you.
So collaboration with industry is always a difficult issue, but I think we managed to do it quite well. So myself, I'm heading a lab called HSN Lab. We have a cooperation with Ericsson for 33 years. So it's we are basically, I could say that we are the the academic leg of Ericsson at the university, and it's very successful. So it's not really in this field of research of AI in transportation, but in general, cooperation with industry is successful if we can find the right way how to engage them with our students to have mutually beneficial topics and projects. So it is more and more difficult these days to find people who would like to start a PhD, let's say, because of several reasons, because what happens on the job market and so on, and we need some industrial partnerships on this, industrial funding for PhD scholarships that are the basis then for future research, and we managed to do that quite well. So that's part of the success, I guess.
Yes, and I can add to that one thing that we keep going to these companies, figuring out what they would need, and have a value proposition for them. What would we offer? We have workshops like this with industry, like this, and Roland especially organizes a lot of these, that the industry also talks, and academia also talks, and we have direct, deep down discussions, because they don't have that much time for research, and we do it for fun even, and so this works this way. For the spin-offs, that's another story. University has to help somehow, and has to have some good patterns also before the front of our eyes. Okay.
My comment would be that at least in Hungary, at least at our university, if a lab wants to survive, you have no choice than to work with the industry, because a large part of our funding comes from the industry. And some academics look at it as some dirty thing, but I don't think it's, if you do it well, you get interesting tasks and challenges from real life. And then if you can solve it after a while, if the solution is very successful, then you cannot do it inside the university anyway. So, like, it's a typical way of spin-offs, that when there is a solution that needs more study and more privacy sometimes, then you start a spin-off. So and it also happens, at least happened to me, for example, that you have a businessman who has an idea to do something, and he comes, looks after expertise and finds at the university. And usually it turns out that very often the original idea is quite naive, but if we sit down and talk for a while, then maybe we can find a solution, and there can be a sort of joint spin-off between the university or researchers at the university and the business person. So there are a lot of ways, and I encourage all who are here, because now you have a very good chance. So young people today, they are open for a lot of challenges, and they have a lot of possibilities. And one thing which I would encourage you is, if you want to be free and not to have a boss who is giving you a very direct instruction of what to do, then come to the university. So the greatest value of the university is freedom. And if freedom is important for you, then come to the university.
Very good words. Maybe some questions on AI, on freedom, on the job market. So I have maybe one conclusion, if I may, is that, and it was already said, that those things that are happening and we have high expectations for, sometimes our high expectations in 2 years are too high, and they are not happening in 2 years. So we are kind of overestimating the impact of things that's happening in 2 years. But, as it was said here, we are always underestimating what's happening in 10 years. Okay? So just keep on working on that. Thank you very much. And thank you for being here. Thank you. Bye. Thank you.
Ez most már az marad örök időkre.
Örök időben.